Welcome to episode 34 of the Pulse of Physiology. I'm your host, Dr. Jim Davis, and today we're focusing on cardiac pacemaker cells, the specialized autorhythmic cells that keep the heart beating. These cells initiate action potentials without external stimulation, which ensures the heart continues to function even if signals from the central nervous system are absent. In our next episode, we'll build on this discussion by talking about heart rate regulation. But for now, let's just dive into how pacemaker cells generate electrical activity and how they compare to other muscle cells. Cardiac pacemaker cells, also known as autorhythmic cells, are responsible for generating the rhythmic electrical impulses that control heart contractions. Unlike contractile cardiac muscle cells, pacemaker cells contain minimal myofilaments and are not designed to produce force. Instead, their primary role is to initiate action potentials which set the pace for the heart's electrical conduction system. These specialized cells are located in key areas of the heart's conduction system. There's the sinoatrial or SA node, which is the primary pacemaker of the heart, and this is located in the right atrium. Then there's the atrioventricular or AV node, which is a secondary pacemaker and is slower than the SA node. And then there are Purkinje fibers and other conducting cells. These are tertiary pacemakers that take over if higher pacemakers fail. Now, cardiac pacemaker cells differ significantly from skeletal muscle cells in several ways. Cardiac pacemaker cells generate spontaneous action potentials, whereas skeletal muscle cells require a signal from a motor neuron. Cardiac pacemaker cells do not require external stimulation, which makes them self-sufficient in generating heartbeats. Finally, cardiac pacemaker potentials drift towards threshold, unlike the stable resting membrane potentials seen in skeletal muscle cells. Now, pacemaker cells exhibit a unique pattern of depolarization due to their pacemaker potential drift. This process allows them to generate action potentials without the need for external input. So let's break down the key phases. So to start off, we have the pacemaker potential drift, also known as slow depolarization, and what I often refer to simply as drift. Now, during the drift, voltage-gated sodium channels open, which allows for sodium influx into the cell. This is important because this slow, spontaneous depolarization gradually moves the membrane potential towards threshold, which ensure the pacemaker cells fire regularly and automatically. The drift phase is a fail-safe mechanism. So even if the central nervous system signals are absent due to injury or dysfunction, pacemaker cells will continue generating action potentials, which prevents the heart from stopping. Then you have depolarization, which looks like a rapid upstroke on the figure of an action potential in a cardiac pacemaker cell. During depolarization, the membrane potential reaches threshold, or when the membrane potential reaches threshold, voltage-gated calcium channels open, which allow for calcium influx. This is important because calcium influx drives the rapid depolarization phase, leading to the initiation of an action potential that spreads throughout the heart's conduction system. Then we have repolarization, which is where the cell resets. During repolarization, voltage-gated calcium channels open, which allows for potassium efflux, which brings the membrane potential back down to its baseline level. This phase is important because it resets the pacemaker cells, allowing the next pacemaker potential drift to begin. This ensures continuous cycles of depolarization and repolarization. So in summary, during the drift phase, sodium influx slowly depolarizes the membrane. During the depolarization phase, calcium influx rapidly brings the membrane to threshold and fires an action potential. And during the repolarization phase, potassium efflux resets the membrane potential for the next cycle. So the drift phase ensures that the heart beats independently of the nervous system. While the central nervous system can certainly modulate heart rate via sympathetic signals, which increase the rate, and parasympathetic signals, which decrease heart rate, pacemaker cells will still function in the absence of neural input. This built-in redundancy is critical for survival. So let's summarize with our 4 key takeaways. Cardiac pacemaker cells generate spontaneous action potentials without needing external signals. The SA node is the heart's primary pacemaker, with backup pacemakers in the AV node and Purkinje fibers. The pacemaker potential drift, or drift phase that allows sodium influx, ensures continuous action potential generation, while calcium influx drives depolarization and potassium efflux resets the cycle. Finally, unlike skeletal muscle cells, pacemaker cells do not require neural stimulation to fire action potentials. And so with that, we are finished with episode 34 of the Pulse of Physiology. I hope this episode has clarified how cardiac pacemaker cells function and why they are essential for maintaining heart rhythm. Join me next time for episode 35, where we'll explore regulation of heart rate and how different factors influence the speed of pacemaker activity. Until then, keep questioning, keep exploring, and stay curious.